Okay, welcome everyone to our session this afternoon is about post-quantum cryptography, and we have three talks. And the first one is defeating low-cost countermeasures against side channel attacks in lattice-based encryption, case study on Crystal Kyber, and Siobhan will give a talk, please.
Hello, good afternoon, everyone. So I'll be presenting this talk on behalf of my colleagues, Prasanna, Thales, Dirmanto, and Jean-Peter. Actually, the work has been done mostly by them, but they could not come here. So I'm presenting on behalf of them over here. So let's start with a bit of context. Although this is the sixth session on post-quantum, but in case you missed it or you didn't attend it, so we know that okay, quantum computers are coming, right? And that can be a threat to cryptography. So therefore, there's a need to migration. Now, when are they coming? There is, of course, too much debate to it, but I have the answer to that. Actually, as of this morning, when I submitted the slides, it's in 5 years, 219 days, 0 hours, 33 minutes, and 1 second. Okay, it's now a few hours less. There's actually awareness campaign that has been started by the Cloud Security Alliance, and they had actually, of course, there's a joke, but they started this as a awareness campaign so that they put a date of April 14, 2030 to like push people's and like some estimate and to also align with some estimates which say that okay, maybe we'll have a quantum computer by that date that is capable of breaking RSA 2048. But even if that is not the case, there is a need for migration, and we can already see, for example, in the recommendation, if we look at the CNSA 2.0, like starting from next year, we should be supporting software and firmware signing if we have to work with, for example, a federal agency or some other applications. And then you see like by 2030, almost everything should be supported for post-quantum or quantum-resistant cryptography. Now, how do we support that? Thanks to the standardization. Now we know, actually, just earlier this month, last month, the first PQC standards were officially released. So for the key encapsulation mechanism, we have Kyber, which is 203. For the signatures, we have Dilithium, Falcon, and Sphinx Plus. We have another round going for KEM for different construction, which includes Bike, Michaelis, and HQC. And then, of course, there are other recommendations coming out from agencies like BSI, which would recommend Frodo KEM and Classic Michaelis for KEM, and XMSS and LMS for digital signatures. We, in this work, will be focusing on Kyber, which is the prime candidate for KEM. But the results that we are presenting might also extend to other KEMs that are based on lattice-based schemes. Okay, so the setting we are in, we have Alice and Bob. So Alice is, they want to share a secret key, like a symmetric key, so that they can do high-speed communication using symmetric cryptography like AES. But to do, they have to do a key establishment. How does it work? Like Alice will do a key generation, a pair of public key and secret key will be generated. Then Bob will use that public key to actually encrypt the message or the shared session key, send it as a ciphertext to Alice. And in the decapsulation procedure, using the secret key, Alice will be able to retrieve the same shared session key. Now, the setting we consider ourselves in is a static key setting, which means that Alice is reusing this key pair for multiple KEM instances, and that is where sidechannel is coming into the play. And the main target where we focus on is in the decapsulation procedure. So that is the part where actually the manipulation of the secret key is happening. And since we are assuming a static key setting, this will be happening over multiple executions. So we target the decapsulation procedure. This is something which has been let's say a hot spot for these attacks. A lot of attacks have appeared in the literature which target the decapsulation procedure. And if we broadly look on the family of these attacks, we can see two categories. One is the known ciphertext attack that basically primarily targets the dot product between the ciphertext U and the secret S. That is also basically targeting the polynomial multiplication. And a bigger family of attacks belong to this chosen ciphertext attack setting, where adversary is trying to craft malicious ciphertext and then send it for decapsulation and then try to recover the key from that. So basically, the key idea is that you would craft a ciphertext which would result in decryption to a message that has a relation to the secret key, or better, a small part of the secret key, so you can do a divide and conquer kind of an attack, and then therefore you can try to recover the key. Now, in the decapsulation procedure, one of the main let's say point of attack is the FO transform, the Fujisaki Okamoto transform, and the reason is that it has multiple operation, and all these operation actually leak in one way or the other. So therefore, you can have attacking like attacks on the decryption procedure that is happening in the decapsulation in the FO transform, the re-encryption, the hashing, as well as the compare. So all these operation can leak in different capacity and have been actually targeted in the previous works. So just to reiterate, so what is happening in the known ciphertext-based side channel? Basically, we have Alice, who is computing the dot product between the ciphertext and the secret key, and so therefore the assumption is that the attacker has the knowledge of the ciphertext that is being used, and on the chosen ciphertext attack, attacker does not need the knowledge to the ciphertext, but is crafting malicious ciphertext of specific structure that can help to actually recover the key while measuring the side channel from the decapsulation procedure. So to counter this, of course, we need countermeasures. And if we talk about countermeasures, I think there's also a parallel session earlier. Masking is one of them. This is, of course, a sound countermeasure, and like will solve this problem. However, that might not always be affordable. We know that the masking is costly, and not application will be able to do that. And as a result, for other resource-constrained scenarios, low-cost countermeasures were actually proposed to prevent such attacks. And in particular, we spotted two such countermeasures. One is the ciphertext sanity check, which means that if we detect any specific pattern in the ciphertext, we can reject it. Okay, or like a decapsulation failure check. So if you're sending an invalid, maliciously crafted ciphertext, that might lead to a decryption failure. And if that happens, one may try to refresh the key, or so therefore limit the attack to a single trace. So if we look at the decapsulation procedure over here, basically the ciphertext sanity check is doing a detection at the input, where, for example, we can detect a low entropy on the ciphertext, and if that exists, we can stop the whole process, or we can look at the decryption failure, and if the failure happens, we can actually refresh the key. Now, what we present in this paper is that we demonstrate novel chosen ciphertext attack strategies against these low-cost countermeasures. So we specifically target these two countermeasures. And what we also came out as a contribution in this work is that we end up developing a novel solver that is based on greedy algorithm, and this improves a lot upon the commonly used belief propagation method in such attacks. So let's look at these countermeasure one by one. So first is the chosen the ciphertext sanity check. So in most of the CCA, that the chosen ciphertext attacks, the ciphertext use has some pattern. Typically, it will be extremely skewed ciphertext, so that would result into a message that is, let's say, all zero, or all zero but one bit, so that it only relates to one coefficient of the key. So therefore, the entropy of this ciphertext is actually very skewed, and therefore, like if you do entropy check, you can completely prevent this attack. Well, that is not true. You cannot completely prevent this attack, and there is a very easy way to actually bypass such countermeasures. So what we do over here is that we take the ciphertext, which is now low entropy, let's say, but we simply mask it with the public key. Now, we have two components of the public key, A and B, and we simply mask the ciphertext with this public key. Now, what happens is that because the public key is uniformly random, the ciphertext now also looks uniformly random. But I don't show the equation here. It's in the paper. But if you just write down the equation and try to derive the message, the public key will actually just canceled out apart from a small error term, and therefore you can still recover the message. So if you're doing a chosen ciphertext attack and you want it to decrypt to a specific message, you can actually still do it, but having a ciphertext here which is uniformly random in nature. So, but to apply it on Kyber, we tried to solve two practical problems, which, so as the attack was not possible out of the box. So one was that the size of U is not equal to A. U is a vector, A is a matrix. So basically we can pick any of the rows of U and apply, of A and mask, apply it as a mask to U. Okay. And what is interesting here is that we don't have to we don't have to limit ourselves to only adding the public key. We can add even multiples of public keys. So like K times public key can also be added. And since it will all cancel out, so the attack remains exactly the same. The other thing is that the ciphertext is compressed, which means we do not have, let's say, so we cannot exactly input the ciphertext. So therefore, like sometimes the attack does not work. What we have to do is that we have to simply restart the attack and just use a different multiple or a different row of the public key, and with that, actually the attack works. So we did this experiment on Kyber 768, and we tried to recover 200 different secret keys. And we were able to recover all of them. So 200 independent experiments, we were able to get all of them. And on average, like for, let's say, 100 experiments, we had to run it 173 times to recover the key because of this problem of compression, where we had to restart the attack if, let's say, the attack doesn't work on in one time. For 100 experiments, we had to do and 0.73 times more experiments to actually do a full key recovery. Now moving forward towards the decryption failure check. So normally, if we do a known ciphertext attack, that is done with a valid ciphertext, so it will not result into a decryption failure, and therefore, like it will not this can naturally work against this countermeasure. But of course, like we are assuming that we go into an assumption that the polynomial multiplication operation is protected by masking or some other technique, so that these attacks can be thwarted. So what we want to do here is we want to see if we can adapt the chosen ciphertext strategy, but attack this decryption failure. And to do that, of course, we have to work with a valid ciphertext. So the idea is can we perform a valid chosen ciphertext attack on these kind of on these kind of countermeasure? And this might so what we do is we apply a valid ciphertext, and this will decrypt to a message, and we try to exploit the leakage from the noisy message polynomial that is decrypted and see if we can and from that we try to do the key recovery. There are some challenges. So, for example, we cannot do a standard DPA style attack because for the message, we cannot do a divide and conquer. So every bit of the message will depends on all the coefficients. So that cannot work. And also, although the message will depend on the secret key, the manipulation of it will not depend on the secret key. So the leakage is not there. So how do we do it? We basically do it in these 3 steps. Okay, so we start with a valid ciphertext. We let it decrypt to a valid message, which is noisy, M dash. Okay, so we recover in the first step the Hamming weight of M dash through side channels in a profile setting. Once we have recovered this M dash, we use it to find the error in the message polynomial. That is, let's call it delta M, or what is also denoted as E small in this figure. And we use it to construct linear equality. Now, this inequality, if you check the equations in the paper, will directly relate to SNE, which is our secret. And once we have these inequalities, we can actually feed it to a solver and try to solve it for key recovery. So these are, let's say, how these steps look in detail. So the first step is to recover the Hamming weight of the message, of M dash. We tried 2 different implementations. The reference implementation here, the good thing was everything was running sequentially, and we were processing it was processing 1 coefficient at a time. So therefore, doing it was quite straightforward. But also what we looked at was an assembly optimized implementation. This was processing 10 coefficients in parallel, and therefore this becomes quite noisy. So to overcome that, what we do is like we fix 9 message bits to 1 and 1 message bit to 0. So what we were recovering is every 10th coefficient for that matter. Okay, so we use a simple random forest to do this classification. And for the reference implementation, we got around 91% accuracy in recovering the Hamming weight. And for the assembly optimized implementation, we get around 32%, like 32% accuracy in recovering the Hamming weight. Now, as you will say later, this 32% does not mean that we cannot do the attack. The attack can still be will still result into a full key recovery. It will just need more traces. But although the Hamming weight prediction accuracy is low, this still work out. Now the second step is that like this has of course too many equations, so I'll go very fast with it. But the point that I want to show here is that if you start to write delta m, it turns out to be like a function of ENS, which is our secret that we want. So basically what we want to do is like, we want to find inequalities, how the Hamming weight of M dash results into SNE. And what we basically see here is that if the message bit is 0, okay, the Hamming weight of M dash reveals the sign of delta M. And why is that? Is that when, like if you look at this distribution, when the Hamming weight is low, this means that with a very high probability, the delta M is actually positive. But when the Hamming weight is high, we know for negative numbers, they have a higher Hamming weight, and therefore the resulting delta M is very high. So we can choose the threshold. You can see the dotted vertical line in the distribution. These as the threshold to actually build stronger inequalities. So we are able to recover the sign of them from this inequality. But not only that, we can actually make tighter inequalities, because for every Hamming weight, the range of M dash is also like different, and we can exploit this information as well and feed it to our inequalities, and that actually leads us to a more efficient attack for that matter. Now this is done. Our inequalities are made. Now we can just feed it to the solver. Okay, so the popular approach is a belief propagation algorithm. Like we take, for example, this paper from CHES 2022, and here when we applied it on a setup, this works very well. It takes around 10 minutes for it. So what we also propose in this paper is a greedy search-based algorithm, which actually reduces the solving time from 10 minutes to 20 seconds. And it's also like more easier to understand how we do. This is again, like I will not running out of time, but like basically what we have in our solver is a score function, and basically we use that to build to build this greedy approach. But maybe what I would like to show over here is that you can see the comparison between the belief propagation and the new approach that we get, and of course, like it is much faster. So what we get at the end with the greedy algorithm compared to the belief propagation is that we need much fewer number of ciphertexts. We can tolerate more noise, and we have a much faster solver. So instead of, for this example, instead of 10 minutes, it is around 20 seconds. So we did the experiments like on the STM32F4 board with the PQM4 library. So for the first experiment, we tried 10 different independent experiments, and we were able to recover the key in all of them in around 5,200 traces. Here, what we do is like we try to build our inequalities exploiting leakage from only 8 message bits. Okay, and then what we do is like we take it forward, and we say, okay, on average, like half of the message bit will be 0. So what happens if we try to like build a larger system of inequalities, assuming 128 0 bits? And for that, actually, if we build that like 128 inequalities and feed it to the solver, we can bring down the number of traces from 5,200 to around 325, which is a drastic reduce. On the optimized implementation, since we had a lower since we had like a lower accuracy on the Hamming weight, like we need more traces, but still with 24 times more traces in this case, with around 7,800 traces, we were able to again apply the same attack and recover the key. So like intuitively, it might seem that 32% is a low accuracy, but why this work is that we notice that even if the predictions are wrong, but close to the actual Hamming weight, the inequalities that are generated might still be correct. And that is where like the attack still works. In the paper, you also have some information on how we actually adapt this attack for shuffling and masking. I unfortunately don't have the time for that, but like we can easily like extend it to apply this attack on both shuffle countermeasure as well as masked like masking. By easy, I don't mean like the adaptability of the attack is easy, like the application of attack is easy, but of course you will need more traces to do it. So with this, let's conclude. So we showed basically practical attacks on 2 detection-based side channel countermeasure on Kyber Chem. We report basically attack to circumvent the ciphertext sanity check by simplifying by simply applying the public key as a mask. Okay. We also try to do try to propose an attack on the decryption failure, and which is one of the first attack to actually use valid ciphertext to do a chosen ciphertext kind of an attack. This exploits the leakage from the noisy message polynomial. We also introduce a simpler and improved inequality solver, and as I've shown, like this gives us many advantage in terms of ciphertext, noise tolerance, as well as the time to solve. And finally, we could adapt the attack to apply to both shuffling and masking countermeasure. So thank you, and if there are any questions, very happy to take them.
Okay, thank you for your presentation. Are there any questions for the speaker? Okay, then maybe one quick question. So in some of the slides, you mentioned Kyber 768. Did all of you experiment about this parameter set, or did you try more parameter sets?
No, I think we tried on like also on the other parameters, but what we probably reported here in terms of number of yeah, we tried on other parameters as well, but I think what we reported here is mostly on 768.
What's the trend if you try with different parameters?
We don't see like very so what we are able to exploit very efficiently over here is the message bit 0. So message bit 0 actually leaks more information because it has a stronger bias, like for reasons that are explained in the paper. But and therefore, if there are more messages bit which are 0, we can do a much efficient attack. And that is also like one thing that we kind of try to exploit in the shuffling as well, is to find where the message bit is 0. And by exploiting that, we can adapt it to shuffling, for instance.
Is it working? It's working. Yeah, it's working. Well, thank you very much for your presentation.
Thank you.
Thank you for the technician as well for fixing this. Okay, so let's move to the next presentation. The title, Single Trace HQC Share Key Recovery, which solve analytical side channel attacks. And the speaker are Guillaume and Julian, please.
Okay, thank you for the introduction. So I'm Julien Maillard, and here is Guillaume, my colleague from Université de Limoges. I'm myself from CEALIT in France. And today, yes, we are going to talk about soft analytical side channel attacks on HQC, a post-quantum crypto system based on error correcting codes. So I'm going to start by giving a short introduction for soft analytical side channel attacks. So let's start with the general idea. You have this piece of code here that runs on a microcontroller. On the right side, you have the electromagnetic trace when this code is running. Let's assume now that this code manipulates a secret data. Here it's A, and it puts it in the register R0. Maybe with a little bit of leakage assessment, you can find the time samples where the different variables of this algorithm are manipulated. And if you want to recover the secret, well, you can try to opt for a supervised approach, profile approach, in order to predict the value of A, your secret. But sometimes the prediction you have is not perfect. You have uncertainty, and well, you can think a little bit and see that the other variables here in this code snippet are somehow related to your secret. So you can also try to make prediction on those variables, and you see that maybe having information on C or D gives you information on A too. And the goal of soft analytical side channel attacks is to efficiently compute the probability of A given the probabilities you have on other variables. So to be a bit more formal here, let's take a configuration space in which your variables live, x1 to xn. And let's consider a problem. You have, for example, it's a cryptographic algorithm that manipulates those variables. This problem G is too big for you to compute the marginal probability of each variable as is. But the key idea of factor graphs and belief propagation is to break this big function G into the product of smaller functions. To do so, we use a factor graph, which is a bipartite graph that expresses such factorization. It is composed of two types of nodes, variable nodes and factor nodes that represent the operations that manipulate those variables. The good thing with that is this structure allows you to easily manipulate probability distributions, which are the things we have after a template attack, for example. So on this factor graph, you can propagate the information thanks to the belief propagation algorithm, and you can use, for example, the sum product algorithm to do so. So you can transmit messages from variables to factors. You can also transmit messages from factors to variables. Here are the equations if you are interested. And at the end of the algorithm, you can compute the marginal distribution for each variable by computing the product of incoming messages. It's good to know that this kind of structure allows to do exact inference only on tree-like graphs. Okay, it doesn't work on, well, it doesn't provide exact inference on cyclic graphs. So to wrap it up a little bit, this technique allows to break a high-dimensional problem into smaller problems, a combination of smaller problems, and it's tailored to manipulate probability distributions. It can be viewed as an error-correcting framework, and actually it has been used at the beginning for LDPC codes or turbo codes decoding, for example. While performing belief propagation on factor graphs implies dealing with a NP-hard problem, but the loopy belief propagation algorithm is an iterative algorithm that performs message passing in a certain way, and often gives you a good approximation for the maximization a posteriori problem. It's good to know that several algorithms, crypto algorithms, have already been attacked with soft analytical side channel attacks. It started with the AES in 2014, and following that, there were attacks on Keccak and also Kyber's NTT. When you try to develop such a framework, you need to deal with some technical difficulties that can arise. For example, the size of the alphabet, the number of values that can take your variables can be a problem. The amount of observable variables in your factor graphs can be really big, so you need to be able to scale up with that. And also, as you multiply probability distributions, you can reach numerical stability issues that need to be deal with. Okay, so now I'll let the floor to Guillaume to talk to you about the whereabouts of HQC.
Okay, so I will present HQC, the main ideas, and also the main structures that we will target during our attack. So HQC is a key exchange mechanism. It's a candidate in the fourth round of the PQC NIST standardization process. And it's generated from a publicly encryption scheme with the HHKey transform, which is a Fujisaki Okamoto-like transform. So I just need three algorithms to describe HPC, the key generation, the encryption, and the decryption. So during the key generation, the main idea is to generate a random code H and two secret key X and Y, which are vector of small Hamming weights. And the public key will be the syndrome of these small Hamming weight vectors that are secured with the syndrome decoding problem, the hardness of solving the syndrome decoding problem. During the encryption, you choose a message you want to send, and you will encrypt it with a publicly known code. And you mask this value with random errors. And for the decryption, you use the knowledge of the secret key to decode these code words. So HQC is based on two codes, a random code for the security and a public code for efficiency. And HQC is not based on masking the structure of a code like Bike or classic MakeAlice. So if I want to summarize HQC with a scheme, so you first have a message, you encode it, and then you had an error. The error is bigger than the error correcting capability of the code. And so when you want to decrypt, you first reduce the size of the error, and then you decode the code words. One thing it's important to notice is that during the decoding phase, we already remove the secret key. So we can target this decoding process to recover information about the shared key. So the decoding process of HQC is in fact a double decoder, a concatenated code. So when you receive your code word, you first decode it with an inner decoder, which is the Reed-Muller decoder. And then you obtain an intermediate code word. Then you will decode with the outer decoder, which is the Reed-Solomon decoder, in order to recover the message, which will be the shared key. So yes, we have a property in HQC. We want that the message we decode, the final message, we want it to be the message we send. And we just, the error must be below the threshold of 2 to the minus 128. And this low decryption failure rate implies a decryption failure rate on the first decoder. For instance, the intermediate code word is almost always error-free. We have error just with a probability lower than 2 to the minus 10. So basically, when you want to target the decoder of HQC, you have two choices. You can target the inner code in order to recover the secret key. And you can also target the outer code to recover the shared key. So we will describe how the Reed-Solomon code works in order to recover the shared key. So the first step of the Reed-Solomon decoding is to compute the syndrome of the code words. So basically is nested for loops, which perform a Galois-Field multiplication. So in order to compute the syndrome S, you manipulate the code word C with the parity check matrix H. So in our case, the parity check matrix H is a known value, and we want to recover the value of the code word, which is our secret. So I will explain how we can exploit this structure to build an attack. So based on this multiplication, we can acquire some electromagnetic traces. Here we display the average trace we obtain. And we can perform some leakage assessments. Here we compute the R2 score with the linear regression analysis. And so as you can see, our variables, so the two inputs and the outputs, leaks during these traces. So we observe that there is a asymmetrical leaks between the operand 1 and the operand 2. It's because the implementation of the Galois multiplication is based on the fast Fourier transform, which is in symmetrical algorithm. And the first operand is manipulated with many shifts and binary operations that make leaks the variables. So we can exploit these leaks to perform an attack. So we train a machine learning algorithm, which is a linear discriminant analysis, and we observe that we are able to recover the exact value of the first operand with a probability close to 94%. And unfortunately, these operands hold the secrets we want to recover. So at this time, we don't need any other attack to recover the secret. We just have to gather the output of the machine learning algorithm. So the first countermeasure we propose is just to swap the two operands. Either since A times B equals B times A, we can apply it with no overcost. So for the rest of the presentation, we consider that we did the swap. And for the rest of the presentation, we will exploit the result of the template about the Hamming weight of the output. So now we need to perform the belief propagation attack to exploit this Hamming leakage. So the first step is to build the graph. So we need to identify the target, which is the Galois multiplication, and represent it as a factor graph. So this is an offline task. The second step is to train the machine learning model, as I told before. And the last step is to perform the real attack. So acquire real trace, run the belief propagation, and then extract the probability distribution on the secret. So we are able to represent the syndrome computation as a graph, as you can see on the screen. So we can see the value of the code words C1 to Cn, which are in individual windows. And we can also see the value of the parity check matrix H and the syndrome S. So when we will feed the graph, we will give template inputs to all the outputs of the multiplication. Before showing the result, I have to talk about another strategy, which is a redecoding strategy. As I mentioned before, the intermediate code word is almost always error-free. So after our attack, all the error we have comes from the belief propagation algorithm. And since the Reed-Solomon decoder is a public decoder, we can use it to correct the error occurred by the belief propagation. Unfortunately, for this family of code, we know a better decoder, which are the list decoder, and they have a bigger error correcting capability, and it allows us to perform a strongest attack. So we simulate the template prediction Hamming weight, and we increase the noise step by step, and we obtain this result for the 3 security level of HQC. So since when the noise is small, we obtain a perfect success rate, and when the noise increases, the success rate decrease. And what is funny to notice is that it's easier for us to target the third security level of HQC 256. It's because the size of the matrix is bigger, so we have more information to exploit to recover the secret. Now I will show how we can also target some countermeasures. The first countermeasure we target is the code word masking. So when you want to protect a decoding step, you can first generate a random mask and encode it to obtain the code word mask, and then you decode the sum of the two, and you remove the mask after doing the decoding step. This is possible thanks to the linearity of the decoder. And when you want to recover the code word, now you have to attack both the decoder and the encoder. And this is possible because the encoder of Reed-Solomon code is also mainly based on Galois field multiplication. So we are able to build a graph and run the belief propagation on it. And I display the result here. Oh, I forgot to mention that in the encoder graph, we have many cycles. And as Julien told before, the cycles do this thing. So we are not able to reach a perfect accuracy. That's because of the cycles. And also we cannot reach high noise level with a perfect accuracy because of the less redundancy check. But in a practical attack, we are still able to recover the secrets with a probability bigger than 75%. So it's still a threat for HPC. And I will let Julien talk about how we can target the shuffling countermeasure.
Yes, as we shuffle speakers, we also try to shuffle HQC. Let's start with a typical shuffling and countermeasure that has been proposed for Kyber in 2020. It's called the fine shuffling. The idea here is to randomly swap the operands of the Galois field multiplication. The thing is that in our case, if we perform soft analytical side-channel attacks and considering templates on the outputs of the Galois field multiplications, well, the attack still works. So this countermeasure is not efficient. You can also try to apply the coarse shuffling proposed in the same paper by shuffling the different multiplications in each window of the syndrome decoding algorithm. Here again, if you use the templates on inputs and also on outputs of the Galois field multiplication, this shuffling countermeasure doesn't hold. Details are in the paper. Last, you can try to shuffle the windows, randomly selecting the windows. But here again, if you perform Saska with and afterwards using a solver for the probabilistic assignment problem, well, you can also recover the code word. So that's not efficient enough. On the contrary, what is efficient against our proposed attacks is the full shuffling countermeasure, and as its name implies, you shuffle everything, so the windows and also the different multiplications inside each window. So the algorithm is displayed here. The thing with this countermeasure is that it increases the combinatorial complexity of the attack to way higher than the security level required by the scheme. So seems safe against our attack. Here I just displayed this countermeasure on the decoder, but indeed you can also apply this full shuffling countermeasure on the encoder. You just need to change a little bit the implementation, but it can be done. Okay, so now I take 1 minute to talk about the Fujisaki Okamoto-like transform in HQC. The Fujisaki Okamoto transform performs a re-encrypt operation. And actually with the re-encrypt operation, you have an encoder which is called on the same message. So you can plug the two graphs you had before and try to run the attack. So here is the result of this combined attack. We see that we reach higher noise levels. You have those kind of peaks on the success rate. This is caused by the cycles, which you can find in the encoder graph. But still, you can, if you are on a target with higher noise level, you can try to attack it with the combined attack instead of just the decoder one. Okay, so as a conclusion, we presented a shared key recovery attack on HQC based on belief propagation on factor graphs. So for that, we attacked the decoder and the encoder. We also exploited the Fujisaki Okamoto structure to combine both attacks on the encoder and the decoder. We also showed that code-worm masking countermeasures, as well as some Kyber-like shuffling countermeasures, are not efficient here. But the full shuffling countermeasure is efficient against our attack for now. As a future work, we believe that it is important to carefully select the way of implementing this full shuffling algorithm because it comes at a cost of, for example, generating randomness. Also, all our attacks are based on the exploitation of Galois field multiplication. So you can try to get into masking this Galois field multiplication. This is a research path too. And maybe this kind of attack can be applied on other schemes using the FO transform. And I take 1 second to say that the framework we use to perform these attacks will soon be in open source, so we are very happy about that. And this concludes our presentation. We will now take questions if you have some.
Thank you very much for your presentation. If we have questions from the audience, please feel free to use the microphone in the middle. Maybe I can start with the first one. I understand that so for this presentation is about HQC, but could you please comment on maybe how to extend this to maybe other code-based scheme?
Okay, so in this presentation, we exploit the structure of the code in HQC. And as I mentioned in the presentation, the structure of other code-based scheme like Bike and Michaelis use a masking code structure. So maybe it's not as easy as it can be to transform this attack in another scheme.
Thank you. Any questions from the audience? If not, then let's thank the speakers again. May I have the timer reset as well? Thank you. Okay, let's welcome our third talk in this session with the title Hints from Hertz Dynamic Frequency Scaling Side Channel Analysis on Number Theory Transform in Lattice-Based Schemes. And the speaker is Tianrun. Please, the floor is yours.
And thanks for the introduction. I'm Tianrun Yu, and I'll talk about Hints from Hertz, a dynamic frequency scaling side-channel analysis of number theoretical transformation in lattice-based schemes. And this is a joint work with my advisor, Chi Chen, Zilong Yang, Dr. Yingcheng Wang, Professor Yanbing Pang, and Professor Chen Wong. Right. So let's start with some background. In 2022, a new type of side-channel attack named the Hertz split was proposed. And the reason of calling it a new type of SCA is because it exploits an unusual CPU feature named dynamic voltage and frequency scanning, DVFS. And the original Hertz split attacks shows a remotely extraction key the key inside of the Hertz split attack is that it can turn a power side channel attack into a remote timing side channel attack. And the original work shows that it can remotely extract key from a constant time implementation of a now broken CAM cycle. So how does a DVFS-based Hertz split attack actually works? Basically speaking, almost all inter-CPUs use DVFS to save powers. And under two different workloads, the CPU will adjust its power consumption through frequency scanning. And we all know that power is data dependent, but in the setup of Hertz split attacks, it can shift the dependency to frequency. So in the Hertz split attacks, data is frequency is data dependent, and frequency leaks data. So what's more alarming is that Hertz split actually challenges the constant time cryptography. Imagine a program with constant cycles running on different data, which is data frequency dependent, and it will end up with a different runtime. So in some extent, the Heartbleed attack actually forces us to rethink of the principle of constant time cryptography. A quick look at the state of the art. In 2022, Wang introduced the original Heartbleed attacks, and almost simultaneously, Liu et al. From Intel validates an attack on AES. And in the last year, some attacks on the browser Chrome was conducted, and in this year, Wang et al. Again discovered leakages beyond Sykes and demonstrating Heartbleed attacks into some other cryptography systems and even GPUs. So our motivation is quite simple. We like to see if there is any leak in the lattice-based cryptography, especially the lattice-based games. We choose to exploit the entity-based lattice-based games because entity is power-intensive operations, and our contribution is somewhat first Heartbleed-like analysis. We investigate the potential leakage of entity and validate it with two games, a Kyber and an NCT-RU. So let's have a quick recap of the number theory electric transformation. The entity provides efficient polynomial multiplication. Given two polynomial U and S, entity applies two forward transformation to the both of the polynomial, and followed by a pointwise multiplication, and finally an inverse entity to transform the polynomial back. So this figure shows a simple illustration of how entity is applied in the lattice-based games for decryption. The polynomial multiplication occurs between a ciphertext polynomial U and a secret polynomial S. And to leak about S, we choose to target the inverse entity, and is noted as inf entity. So if I'm familiar with entity, you may recall the butterfly unit or butterfly networks. This figure shows forward CT butterfly for the forward entity and the GS butterfly for the inverse entity. So we mainly focus on the inverse entity. So just take a primary look at the GS butterfly. And another issue is about incomplete entity. And in practice, a common design is to use incomplete entity. It is either because the parameter of a polynomial ring does not meet certain constraints, like the certain rules of unity does not exist, or sometimes the incomplete entity is somewhat more efficient. A typical example of using incomplete entity is Kyber. Also in Kyber rings, the parameter setting does not meet certain constraints, and the isomorphism of the polynomial ring can only maps to a product of 2-degree polynomial rings. So after the entity transformation, the polynomial in entity domain consists of 1-degree polynomials. Correspondingly, the entity butterfly in Kyber stops at a 1-degree polynomials instead of the constants. So what about the inverse incomplete entity? The incomplete inverse entity butterflies also will starts as 1-degree polynomials. So if you may if you see the pictures, you may find out that you have to do twice GS butterflies for the coefficients in the polynomials. you have to do one for the red marked coefficients, and you have to do another for the blue marked coefficients. And just for comparison, we provide a diagram for the a complete entity. And a simple observation is that in Kyber's incomplete entity, the coefficients at even or odd indices are computed separately in an incomplete entity. So it leads to our basic ideas. What if the coefficients of the odd or even indices are all zero? It will list output. It will list half of the coefficients of the outputs to zero, and it will trigger a low Hamming weight. Otherwise, it will trigger a random Hamming weight. So how do we let the output of the inverse entity becomes like half zero? The first thing we need to do is get a controllable F polynomial. The way we construct it is the first two elements are set to non-zero coefficients, and all the other terms are set to zero. And this is how the Hamming weight differences propagate. Hamming weight difference propagate, and you may notice that the in the random Hamming weight cases, Hamming weight differences propagate twice as much as the low Hamming weight cases. And apart from the Hamming weight differences in the output, there is also Hamming weight differences through the propagation, like in the intermediate layers. So what about the frequency? What about the frequency? If we observe the running frequencies of the two different cases, we may find that the yellow bar corresponds to the low Hamming weight cases runs at a higher level. And the AVAX2 implementation of entity with higher workloads may lead to a much more significant of frequency differences. If we translate these frequency differences into a timing difference, we can observe about like 0.5 milliseconds in a fixed iteration, like 10,000 iterations of entities. So does this leakage still remains in the lattice-based games? So our first goal is to exploit the CPA-secured Kyber without compression and decompression. The reason why we choose the CPA-secured Kyber is that we do not want to introduce the FO transformation, which contains re-encryption. There is a lot of other entity and entity operations. And the reason we also remove compression and decompression is because it is hard to bypass them. If you want to construct a certain polynomial in entity domain, it is really challenging to not removing them. So after removing the two functions, the cipher construction is really simple. You just construct follow the basic ideas and set the first two coefficients as 1 and z, and all the other terms as 0. And then you perform a schoolbook multiplication before the inverse entity. And since all the other terms are set as 0, there are only two coefficients of S is involved in calculation. So this allows us to target different pairs of coefficients in S. And what will happen if we enumerate the value of Z? And this is an experiment result. It aligns well with our basic ideas. There are 2 points marked in red, which correspond to the low Hamming weight, and it runs at a higher frequency. And the other blue points are just random Hamming weight cases, which runs at a lower Hamming frequency. So the step 1 is to choose a ciphertext in this form, and we enumerate the value of Z and collect the frequency, and you may get the leakage point and find out the value of Z. And the second step, the next step is to change the ciphertext with the predetermined value of Z. And this allows you to attack a different pairs of the polynomial S. So since you got all the liquid values of these, does this help you to recover the secret key? The answer is no. You can just, so if you see the equation, you can just get a linear equation about S hat, which equals to 0. And all these linear equations are in entity domains. So a final step is you need to multiply an entity matrix with these linear equations, and you get the linear combination of the original S. But you can still get the you can still not get the value of S itself. But this attack can only take us so far, I think. So what about another scheme like NTTRU? It is more promising since in the NTTRU's decryption, CPA decryption, you may find there is only one operation that is inverse entity. So there is basically no other noises were included, and also there is no compression and decompression. So it is like a perfect goal for us to tap. And in this case, we can even attack the CCA secured entity RU decryption decaps functions, and the experiment result is kind of similar. So in both cases, we can still not get the value of the S. We just get the equations of the coefficients. And so so some may ask, why not just solve them with equations? And the most straightforward way is to use lattice reduction. And luckily, we can follow the work attachment introduced in 2020, and we can use DSDGR frameworks to model the leakages as hints and integrating the hints into the DSDGR frameworks and to quantify the security loss from the side channel leakages. And this is the experiment result. For the 3-parameter set of Kyber, we achieve like 49-bit, 69-bit, and 87-bit of security loss, and we gain a 40-bit security loss for NTTRU. All these Kybers are modified Kybers. So it seems like we still get a long way to actually recover the secret key. So how far is we use these type of attacks to recover the secret key? We did some interesting toy example experiments. Like if we apply our attack on a weekend parameter toy example like Kyber 256, and the ring is like this. And this, for example, uses 6 layers of incomplete entity. And one interesting thing is you can just use our text to gain the hints and recover the private key because the security level itself is not high. So after the security degradation, you can just solve the secret key. But and follow the work of May et al. We find out that for the current parameter of Kyber, we still need about like 60% more hints to achieve an end-to-end attack. So this concludes our work. Our work is not yet practical, but I think the frequency-based side channel is somewhat initiate. And currently, our methods can be adapted to some other entity-based elastic schemes. And there is a lot of future works to do, like it includes attack against CCA, Kyber, or and if you can provide a more efficient way to bypass compression or decompression, it helps to a lot in many attacks against entity. And the final issue, future work might be the balance the attack cost and the accuracy stuff. And thanks for the attention. I'm happy to take any questions.
Thank you very much for your presentation. Do we have questions for the speaker? Yes, please.
Hi, thank you for the talk. This is Toon from PQ Shield. I was wondering about something which is actually on the future work slide now, which is that typically attacks on these lattice-based schemes involve the FO transform, right? And you mentioned it as future work. Do you think that would be easier or harder than targeting the entity? Or maybe to paraphrase, why not go for the FO transform directly?
So you're asking why not attack NTRU? Is that? I'm sorry.
Why not target the FO transform,
FO transform
instead of the NTT?
Yeah. So actually, the attack we currently relies on the controllable polynomial f. And in the FO transformations, I think there is a hash functions which we control the input polynomials into the in the re-encryption steps. So I think it is almost impossible to craft arbitrary input for the entities in the re-encryption. So does this answer your question?
Do we have other questions from the audience? I have one question. So in the end, you mentioned about end-to-end toy examples, and I'm wondering how difficult it is to make it to a real attack, not just toy example.
Okay. So our attack can only achieve, like a security declaration, but you can still exploit more hints in our attacks. Our attacks just take first steps, but in the frequency based side channels, you can still go deeper. I think maybe I just apply the attack to the first layer of the entity. Maybe there is a second layer leakage, maybe. So you may go deeper, or you can combine our attack with some other leakage points. And with more hints, it is able to achieve an end-to-end attacks with lattice reduction, I think.
Okay, thank you very much. So let's thank the speaker again. And we now have time to switch track, and thank you for joining this session.